Okay, so on the thermal side now, let's maybe develop that kind of approximate model again. We keep doing this. We go through approximate models and then the exact models. But again, the approximate models are used to help us understand what to expect. So let's say we want to model the boundary layer growth and be able to predict the position at which the flow becomes thermally fully developed, that XFDT. How would we do that? So let's start back. We'll go through this kind of quickly. We'll start back with our delta T, our thermal boundary layer, assuming laminar flow is approximately equal to 2 square root of alpha T, which is approximately equal to 2 square root of alpha x over u infinity. So let's see. We can go through this and say delta T laminar is going to approximately be dH over 2, just by geometry. And then that's equal to the right-hand side. So let's say that's approximately equal to 2 square root alpha. And we're trying to, again, solve for XFDT over U M. Sorry, this up here should be U M. The mean velocity. Okay, so with that, we can start solving for XFD and do a little bit of algebra. So let's say dH squared over 4 is equal to approximately 4 alpha x FD t over um. So I just squared both sides. And then solving further, we would get what? XFD t over d sub h is approximately d sub h times um over now 16 alpha. Let's multiply by nu over nu. And then this becomes 1/16 dH nu over alpha. Dh over nu. So okay, this here is Reynolds in terms of dH. This here is Prandtl. Okay, so that just says what? That says XFD t over d sub h is equal to 0.063 times Reynolds in terms of dH times the Prandtl number. So probably could have guessed that that was where that was going to end up. This is the exact same relationship for the momentum boundary layer, right? This part in terms of the Reynolds. But how is it related? For a thermal boundary layer, well, it's multiplied by the Prandtl number. Okay. Let's see. Yeah. Say it again. It's the hydraulic diameter. In this case, we're assuming it's the same thing. So the hydraulic, what I mean there is the hydraulic diameter is a geometric thing that's related to the momentum boundary layer. We're assuming in this formulation that the entire parameter that you use to compute dH is thermally active. Okay. So we have this. What do we do with it? We want to maybe understand the relationship between the thermal and momentum boundary layer, the point at which flow becomes fully developed. So if we just look at the definitions here, we're saying essentially that XFDT over XFD m, the momentum, I guess we called that h before, but it's the same thing, momentum, is equal to the Prandtl number. Okay, so think about that a little. Now we have like 4 definitions of Prandtl number, right? So a Prandtl number is at its core a molecular diffusion property, right? It's a property of the fluid related to the thermal diffusion and the viscosity diffusion. So before we said, okay, its Prandtl number is nu over alpha. So nu is the momentum part, alpha is the thermal part. Here it's flipped. So why is that? Well, let's maybe quick sketch out what we're looking at here. So we have, again, flow. and we have maybe flow developing. So if let's draw it this way. So if I'm the momentum boundary layer and I grow like this, right? If you are growing that quickly, and maybe we have a different thermal growth rate for the thermal boundary layer, so maybe that looks like this. So maybe this is our thermal delta T, this is delta M. What is it that governs the growth? So if the growth of delta M is faster than the growth of delta T, that says that effectively nu is greater than alpha. But if it's a faster growth, then that just means that the point at which flow becomes fully developed is sooner, right? So that's the only reason why it's flipped. So here we would just say this is our XFD momentum, or H we've called it. This is XFD T. So you can use this definition, just remember that it's inverted. Okay. Any questions on this stuff? Right. By the way, what did I draw? Which case did I draw? Is this Prandtl is greater than 1, or is it Prandtl is less than 1? PR.
Greater than 1?
Yes. Thanks, Rob. Because our nu is greater than our alpha. Okay, so let's look at turbulence for a second here. We've been kind of talking about the laminar part and how thermal boundary layers behave there. For thermal, let's say we've again got flow. So draw this flow condition one more time. So we've again got flow. We have, let's say, flow that's developing here. Come on. So let's say the thing I've drawn here is our, delta M. Let's also say we've got thermal development, but the thermal is something less. So it's growing at a lower rate, like this. At this point that I've left it off, let's say this is X critical. So at this point, flow becomes turbulent. What is going to happen to the thermal boundary layer, and what's going to happen to the momentum? Well, maybe the momentum part is pretty easy. We've decided we're just now transitioning to turbulence. So the momentum boundary layers are going to grow together pretty much immediately. What about the thermal boundary layers? Right, so think about that. So remember what we said about the mechanisms of transport in turbulent flow and the effective Prandtl number in turbulent flow. In turbulent flow, the mechanisms of moving heat and mass are the same. You have bulk movement of fluid. So even though my diffusive properties are very different in this laminar region, it doesn't matter anymore in the turbulent region, because all of a sudden, everything's moving together. And so that thermal boundary layer will essentially grow exactly at the same rate as the momentum boundary layer. And it'll become fully developed at the same time. Okay, so this is our, This is our delta T. And then this is where things become XFD for turbulent flow. So we can say like XFD turbulent, we don't actually have to specify if it's thermal or momentum because it's the same thing, right? Turbulent, fully developed is going to happen at the same time, roughly. Okay. Yeah, I guess any questions on that? Nope, all right. So keep moving one sketch on a slide at a time, I guess. All right, so what do we want to talk about here? Let's talk about the idea of local versus average. So this is actually a really important thing, and it's another thing that seems like it should be fairly straightforward, but I guarantee everyone at some point will mess it up. So maybe pay close attention to this one. So what you have to deal with developing flow and internal flow is the distinction between the fully developed, say, Nusselt number, the local Nusselt number, and the average Nusselt number. And they're all different in like subtle ways. So we have this, hard to see, but let me just trace over it. You have this thermal boundary layer that's growing here. If I want to compute the local Nusselt number, right, so that would be Nusselt in terms of dH for this, that's going to be H times dH over K, right, where H is something that I'm evaluating at each position. Right? We might even say that that's like H at some position X. So that's my local Nusselt number. If I wanted the average is going to be the integral. So that would be, let's say, Nusselt bar dH would be H bar dH over K. Right? And H bar and H are different things. H bar, HX, like that, they're different even, like, so say it this way. H bar is not necessarily HFD either, your fully developed heat transfer coefficient, because you have that entrance region that could be important. So to evaluate H bar, of course, you would just say H bar is equal to the integral 1 over L of H, which is a function of X times dx. So I'm going to take my length averaged heat transfer coefficient, and that becomes my average. So let's plot out, maybe just to give you a concrete example what this looks like. So we have, as a function of position X, the Nusselt number. So first, I guess it makes sense to plot the local Nusselt number. Let's maybe say that we have flow becomes fully developed, so X, F, D, T here. Let's assume this is laminar the whole time. So starting off, we would have our local. So local is going to go, it's going to be infinite, and it's going to drop down, and at some point it's going to become fully developed, and then it becomes constant. That's local, which we would call what, Nusselt dH. What about the average? So the average always has to take the integral from 0 to L, I guess. So I should maybe write that in the integral. This is the integral from 0 to L. So we're going always from 0 to L, remembering that at 0, my local heat transfer coefficient is approaching infinity. So you're going infinite value here. You have to include that in the integral, and then you're including stuff that's like less than that. So I guess the question is the average Nusselt number going to be greater or less than the local Nusselt number? Greater, right? Because you're including in the integral always something that's bigger than your current endpoint. So the average would look something like this. So let's say it's going to look something like this. And then what happens, so let's say this is my Nusselt bar. What happens when the flow becomes fully developed? How does my Nusselt average change, or the behavior change? Like, what's it going to do? It keeps decreasing, because you keep adding in bits that are lower than what you already have. So it will keep decreasing, and it's sort of continuous in the way it does that. Right? Like this. I didn't intend for that to be linear. Actually, sort of is curved. So it's going to come down like this. So let's see. As we go to greater and greater values of x, we go out towards infinity, these two will eventually perfectly agree with each other, more or less, right? But even if you're relatively far away from the fully developed region, you could still have a significant difference between the average and the local, because your entrance effects can be important. So the mistake that I have said that everybody will make is, I'll say, okay, you've got flow, in a relatively long pipe, what's the new salt number? And people will immediately say, oh, I know the new salt number for fully developed flow. It's 4.36, right? And they'll put that in. And that neglects the fact that at the entrance region, it's not that, right? So the fully developed new salt number, fully developed shear stress, those are not the same as the average.